In this session, we'll take a look at limits. And as we start our journey into calculus, limits is one of the first concepts that separates algebra from calculus. Algebra is known to be static, which means it doesn't change. And calculus is known to be dynamic, which means the mathematics change. So let's take a look at an example. Here we have the function f of x is equal to x squared minus 1 divided by x minus 1. As we read this graph from left to right, as we read sentences from left to right, notice that there is a hole or point of discontinuity in the graph as x approaches 1. So from an algebra standpoint, let's say if we were asked to find f of 1, right, I would simply substitute 1 into our function wherever we see x, and we have 0 over 0, which is undefined. So algebraically, when x is equal to 1, the value is undefined. Now in calculus, and this is just a fact, the limit is the value near a point and not the value at the point. So in calculus, let's say if we wanted to find the limit as our function, which is x squared minus 1 divided by x minus 1 as x approaches 1. So in calculus notation, this arrow that you see, that means approaches. So we take a look at the graph, and as x approaches 1 from the left, notice that the y value is 2, and as x approaches 1 from the right, notice that the limiting value is 2. So algebraically, f of 1 doesn't exist, but in calculus, the limit as x approaches 1, that's going to equal to 2. Now we're going to take a look at this on the calculator. So I'm on a graph, so I'm going to go on to y equals, and we have x squared minus 1 divided by x minus 1. And if I graph, all right, here's our graph. So notice I don't actually see the point of discontinuity or the hole in the graph. So I'm going to go into the table. So I'm going to hit second and graph, which is table set. And notice at 1, there is an error. Okay. Just to see this in a little bit more detail, I'm going to go into table set. So I'm going to hit second and window, which is table set. I'm going to start at positive 1. And now my table, delta table, is the change in the x values on your table. The values are going in increments of 1, 1, 2, 3, 4. I'm going to put in 0.001, and I'm going to hit enter. And now I'm going to go back to the table. So if I hit second and graph, which is table set. All right, so notice as we approach 1 from the left, notice our value at 1 is actually undefined, but notice that our y value, okay, and the y value is actually the limit. Notice that it approaches 2, And as we approach 1 from the right, okay, so here again, notice at 1 it's an error, but the y value approaches 2. So the limit is the value near the point and not the value at the point. So with that being said, we're going to take a look at the limit laws. Right? So here are the limit laws. So notice that the limiting value is actually what the graph approaches, and the limit is on the y-axis. So here's the sum rule, and it says that the limit as x approaches c for f of x plus g of x is equal to L, which would be the limit for the f of x function, plus m, which would be the limit for the g of x function. So the limit of the sum is basically the sum of the limits, which actually means that you can take your limit and you can distribute between sums, differences, products. There is a constant multiple rule, which simply states that you can pull your constant in front of your limit operator, and we'll take a look at that. And lastly, or next to last, excuse me, the limit of the product is the product of the limits, and the limit of a power is the power of the limit. Okay, so basically in each one of these formulas, you can distribute your limit operator. Now we'll just take a look at finding polynomial limits with finite limits. So the first strategy is to substitute. That should be your initial strategy whenever you're asked to find the limit of a finite polynomial. So when I actually say finite limits, a finite limit is a limit that approaches some constant. The first thing you'll do is you'll substitute that constant into your function. Second strategy is to factor, cancel, then substitute. The next is to rationalize any numerators and or denominators, then substitute. And the fourth strategy is to use something called L'Hopital's rule, which is beyond the scope of this course. So let's take a look at some examples. So here's the first example. We're asked to find the limit of f of x if x is equal to 2x minus 3 divided by x minus 2, and we're asked to find the limit as x approaches 1. So the first thing you should always do is substitute. So here I'm going to substitute 1 into our function. So this is 2 times 1 minus 3 divided by 1 minus 2. So in the numerator we have 2 minus 3, which is negative 1. And in the denominator we have 1 minus 2, which is negative 1. So our limit is 1. So let's take a look at this next example. We're asked to find the limit of f of x if f of x is equal to the square root of x minus 3 divided by x minus 9. So here again, the first thing we're going to do is substitute, and in this case we're going to substitute in 9. So the limit for the square root of x minus 3 divided by x minus 9 as x approaches 9. So I'm going to substitute. So that's the square root of 9 minus 3 over 9 minus 9. Okay, the square root of 9 is 3. Right? 3 minus 3 is 0 over 9 minus 9, which is 0. Now, algebraically, this is undefined. But in calculus, this is something that we call indeterminate form. And it doesn't mean that the limit doesn't exist. It simply means that we need to find another way to solve it. So keep in mind our strategies. We tried to substitute. You can factor, cancel, then substitute. You can rationalize denominator, rationalize the numerator. And then there's something called L'Hopital's rule. So in this case, we're actually, and there may be some trial and error to this. So in this case, it may not be so visible, but you can factor the denominator. So here we have the limit as x approaches 9 for the square root of x minus 3 divided by x minus 9. I can actually factor the denominator. I can factor the denominator as the square root of x minus 3 times the square root of x plus 3. So keep in mind, if I were to multiply the square root of x minus 3 and the square root of x plus 3, if I were to multiply or four of those together, I would in fact get x minus 9. So now that I've factored, I can cancel, right? My factors of square root of x minus 3 is going to cancel. So now I'm left with 1 divided by the square root of x plus 3. Now I can substitute. So I can substitute x for 9. And I get 1/6 as the limit. Okay, let's take a look at another example. And here we're asked to find the limit as x approaches -3 for the function x cubed plus x cubed plus 4x plus 8 divided by x plus 3. So I'm just going to write this out. This is the limit as x approaches -3 for x squared plus 4x plus 8 over x plus 3. Now in this case, I'm actually going to involve the limit law so you can see how these things play out. But I didn't actually use the limit laws for those first two problems and explicitly writing them out. So by using the limit laws, the limit of the quotient is the quotient of the limit. So I can actually distribute the limit between my numerator and my denominator. So this is the limit as x approaches -3 for x squared plus 4x plus 8 divided by the limit as x approaches -3 for x plus 3. Right, that's the quotient rule. Next, I can distribute my limit. Okay, now in practice, I wouldn't actually want you to write all of these things out, but I just want you to know that those limit laws are implicit in you working them out without actually breaking everything down to its simplest forms. So in the numerator, I can now distribute the limit. So this is the limit as x approaches -3 for x squared plus the limit as x approaches -3 for 4x plus the limit as x approaches -3 for 8. I'm just put all these arguments in a set of parentheses. And then I'm going to distribute the limit in the denominator. So this is the limit as x approaches -3 for x plus the limit as x approaches -3 for 3. So I've used that sum and difference rule. So now we're going to substitute. So for this first term in the numerator, I'm going to substitute -3 for x. So -3 squared is 9. Plus, I'm going to substitute -3 for x in that second term. 4 times -3 is -12. Plus, There is no x on this last term to substitute, so the limit as x approaches -3 is 8. I'm going to divide that by -3 plus 3. So here we have 9 minus 12 plus 8. So that's going to give us 5, right? Because that's 17 minus 12, which is 5. -3 plus 3 is 0. Now, I don't have 0 over 0. Now, if I had 0 over 0, I would have indeterminate form, and I would look for another way to find the limit. But since I don't have that form, the limit here does not exist. Right? So in this case, the limit does not exist. All right, now we're going to take a look at one-sided limits and limits at infinity. So I'm going to take this function, f of x is equal to 1 minus x. And just to get a visual, I'm going to graph that on the calculator. So I'm going to go back to y equals, clear that out, and I have 1 divided by x. And I'm on a graph. All right, so notice the graph. It looks like this. All right, so we're going to pull some facts that are going to follow us as far as the limits are concerned. All right, so let's find the limit as x approaches infinity, right? That's positive infinity for 1 over x. So you'll notice here that this is an infinite limit because x approaches infinity and not some number. All right, so what does this actually mean? Well, if you take a look at the graph, and the graph actually represents x, and infinity means, so like on our graph, we have negative infinity and positive infinity to the right, negative infinity to the left. That means as x gets bigger and bigger and bigger and bigger, it gets bigger and bigger, and it never stops and it never ends. Right? So as we take a look at this graph, as x approaches positive infinity, notice that it approaches the y-axis, but it'll never actually touch the y-axis. And the equation for the y-axis is, or excuse me, it'll approach. So notice that as x gets bigger and bigger and bigger, it's going to approach the x-axis. The equation for the x-axis is y is equal to 0. So as the limit of 1 over x approaches infinity, that actually has a value of 0. The same thing is true for the limit of 1 over x as x approaches negative infinity. So notice as the x value gets smaller and smaller and smaller, the same thing happens. It approaches the x-axis, but will never actually touch the x-axis. So the limit of 1 over x as x approaches negative infinity is also 0. Now you can see these things mathematically. So if I were to take, let's say the limit of 1 over x as x approaches positive infinity, and if I take the function 1 over x, and I'm just going to put bigger and bigger and bigger values for x, and we're going to see what happens. So that could be 1 over 1, 1 over 2, 1 over 3, 1 dot dot dot, 1 over 10, 1 over 100, dot dot dot, 1 over 1,000. That's going to keep on going forever and ever. Notice that these values are getting closer and closer and closer to 0. And the same thing happens for the other half of this. The limit of 1 over x as x approaches negative infinity is also 0. So these two things are facts. All right. Now I can actually look at that on the calculator. So I'm going to go back into table. And I think here I'm going to change my table set value. So I'm going to start this at 0. And I'm going to make my increments 1. Okay. So if you don't reset your table set, okay, it's going to have whatever you have if you changed it. Okay, so I'm just going to change it back to the default. And now if I hit table, so this is what we're going to notice. Notice that when x is equal to 0, right, there is no value. Okay. As we put in bigger and bigger and bigger numbers, so x, so like for this example, so 1 over 1 is 1, 1 over 2 is a half, 1 over 3 is a third, so on and so forth. So just notice what happens. It gets closer and closer and closer to 0, but will never actually hit 0. The same thing happens as x approaches negative infinity. I'm going to scroll up. So notice that the values get smaller and smaller and smaller. All right, they're just negative, but they get smaller and smaller and smaller, and they approach 0. Keep in mind that 0 is neither negative nor positive. Okay, so even though we have negative numbers, as the numbers get smaller and smaller and smaller, okay, 0 is neither negative nor positive. All right, so these are facts. All right, now we're going to use those facts to find infinite limits. So here's the strategy. We want to divide by the variable of greatest degree. So if we look at this function, 8x squared plus 2x plus 5 over 3x squared minus 2x plus 2, we see that the variable is x, and the greatest power of x is the second power. So I'm going to divide every term by x squared. Right? So this is the strategy you use when you find infinite limits. So I'm going to write this out as the limit for the limit as x goes to infinity for 8x squared over x squared plus 2x over x squared plus 5 over x squared divided by 3x squared over x squared minus 2x over x squared plus 3 over x squared. So we simply divided everything by the variable of largest degree. So now we're going to reduce. Okay, so I'm going to write out the limit laws, and then we'll take a look at in the next example where those limit laws are implied. All right, so the x squares are going to cancel. So that's the limit as x approaches infinity for 8 plus the limit as x approaches infinity. The x in the numerator will cancel one of the x's in the denominator. So that's the limit of 2 over x plus the limit as x approaches infinity for 5 over x squared divided by, so here again, the limits, the x squared is going to cancel. That's the limit as x approaches infinity for 3 plus the x in the numerator will cancel one of the x's in the denominator, okay, and that's a minus, excuse me. The limit as x approaches infinity for 2 over x plus the limit as x approaches infinity for 3 over x squared. Now in practice, it's not necessary to write all of these steps out, but I'm just showing you how those limit laws work. All right. So next I'm going to use the constant multiple rule just to show how that applies. So that's the limit of 8 as x approaches infinity. I can pull my constant in front of the limit operator. So notice the constant here is 2. So I can write this as 2 times the limit as x approaches infinity for 1 over x plus, I'm going to pull 5 in front of the limit operator, and I have 1 over x squared. Okay. And in the denominator, that's the limit as x approaches infinity for 3 minus 2 times the limit as x approaches infinity for 1 over x plus 3 times the limit as x approaches infinity for 1 over x squared. And now we'll simply find the limits. So the limit as x approaches infinity for 8, that's going to give us 8, right? Because there is no x to substitute in a function that gets bigger and bigger and bigger, right? And if you were to graph f of x equal to 8, that would just give you a straight line at 8. The second term, the limit of 1 over x is 0 for my facts, plus 5 times the limit as x approaches infinity for 1 over x squared. So now 1 over x to any power is 0. So keep in mind as x gets bigger and bigger and bigger, the limit of this function is still 0. Divided by 3 minus 0 minus 0. All right, because those limits are 0. So our limit here is 8/3. And we can actually graph. And if you were to graph this function, you would see that when x is approaching 8, or x is equal to 8/3, all right, we'll see that that's the limit. All right, next we're going to take the look at the limit of a graph. Now we've seen the limit of polynomial functions, but now let's look at the limit of a graph. So this rule is very important, and it says that the limit of f of x is equal to L as x approaches C if and only if now here you see the limit of f of x equal to L as x approaches C minus. So what this means is as x approaches some constant from the left. So this is the left-hand limit. It also has to approach the same value. And the limit of f of x is equal to L as x approaches C plus. So that means as x approaches that constant from the right. So this is the right-hand limit. So what this means is that the left-hand limit and the right-hand limit must be equal in order for the limit to exist. So let's take a look at an example, or a few examples. So for this function, we're going to find the limit for this function f of x as x approaches 1. Okay. So now in order to see if the limit at 1 exists, we have to find the left-hand limit, we have to find the right-hand limit, and if both of those limits are the same, then the limit would exist. All right. So first, let's find the left-hand limit. So this is the limit for f of x as x approaches 1 from the left, right? So what does that mean? So let's approach 1 from the left, and as we approach 1 from the left, notice that our limit is 2. So the left-hand limit is 2. Now let's find the right-hand limit. So this is the limit for the function f of x. So notice they don't give us the function f of x. So we're going to just simply write as f of x as x approaches 1 from the right. So we're going to approach one from the right, and as we approach 1 from the right, notice that that right-hand limit is also 2. Since the left-hand limit and the right-hand limit are equal, then the limit for f of x as x approaches 1 is 2. Now, if the left-hand limit and the right-hand limit are not the same, then that limit does not exist. But in this case, both left-hand and right-hand limits are the same. So let's take a look at this example. F of x is equal to x squared minus 1 over x minus 1. And we want to find the limit as x approaches 1. So notice in this example, the limit, now even though they do give us the function x squared minus 1 over x minus 1, I'm going to simply write it as f of x. So notice the left-hand limit is 2. Now if we find the right-hand limit, notice that that limit is also 2. So the limit for f of x as x approaches 1 is also 2. Right? So if you're looking at a graph, you must analyze both the left-hand and the right-hand limit. So let's take a look at this example. All right, we have the function y is equal to x divided by the absolute value of x. So let's take a look at the left-hand limit. So if we take a look at the left-hand limit, excuse me, this is as x approaches 0 from the left. So as we approach 0 from the left, notice that the left-hand limit is -1. Let's find the right-hand limit as x approaches 0 from the right. So notice that the right-hand limit as we approach 0 from the right is +1. Since the left-hand limit and the right-hand limit are not equal, then the limit for this function as x approaches 0 does not exist. And let's take a look at one more example. All right, so here we're gonna find the limit as x approaches 1. So we have to find the left-hand limit, the right-hand limit, and then determine if the limit exists. So this is the function y is equal to 1 over x minus 1. So the left-hand limit, the limit of f of x as x approaches 1 from the left. All right, so as we approach 1 from the left, notice what happens. There's not an actual value, but you'll notice as you approach 1 from the left, the graph is tending toward negative infinity, right? Because it gets smaller and smaller and smaller. This red line is actually an asymptote. And from college algebra, if you're dealing with horizontal or vertical asymptotes, which this is a vertical asymptote, your graph will get closer and closer to that asymptote, but will never ever touch it. So the left-hand limit is actually going to be negative infinity, right? Because the graph gets smaller and smaller and smaller, and it never stops and never ends. Let's take a look at the right-hand limit. The limit for f of x as x approaches 1 from the right. So notice if we approach 1 from the right, the graph tends toward that asymptote, and it gets bigger and bigger and bigger. So the right-hand limit is actually positive infinity. Since the left-hand limit and the right-hand limit are not the same, the limit for f of x as x approaches 1 does not exist.